Yeah, as Nathan introduced me, my name is James Lee, and it's my pleasure today to present to the audience at Data Science Dojo about data ops for the modern computer vision stack. So just a little bit about myself. I my expertise really lies in this whole new field of machine learning infrastructure, also known as MLOps tooling. Currently, I'm a data advocate at SuperAI. I did a lot of writing and speaking at events and with the goal of like driving product awareness for the company. I also, write a lot. I have a personal blog on Medium that basically cover different industry application, research areas in machine learning, and advice from practitioners in the field. And finally, I also have a podcast actually when I interview people like practitioners, researchers in ML and data to unpack their career lesson along the way. Before all of that, I complete my graduate degree in computer science from RIT, where I did some research work on deep learning and recommendation system. And before that, I was in data science doing stuff for fintech and e-commerce startup. And some of my other interests besides just ML infrastructure, just fundraising, venture capital, and community-led growth. I think two of these areas that are very relevant to the world of startups. So this is like a brief agenda of what I want to talk about today. First I will define what is DataOps. Second, I will give a couple of reasons why we need to bring DataOps to the field of computer vision. Third, I will unpack some of the key principles of DataOps. Fourth, I will propose an ideal DataOps pipeline for the computer vision stack. Fifth, I will talk about the several challenges related to data that any computer vision teams have to deal with. And finally, I will talk about the future of the modern computer vision stack. So yeah, let's get started by seeing what is DataOps. So essentially, DataOps is a term that being borrowed by the field of DevOps. DevOps is the transformation in the delivery capability of software teams, and then DataOps focused on the transformation in the delivery capabilities of analytical teams. And as you see here in this image, DevOps is sort of the synergy between engineering, QA, and operations, right? And the goal is they can collaborate together to release the software in a faster pace. And then DataOps is like adding an additional layer of data on top of all that. It bring about different data teams to work at various level to check data quality, engineering data, ensuring data security, with the eventual goal to obtain actionable insights from data they have. And I believe that's similar to how DevOps has transformed the way in which the software development lifecycle works. I think DevOps is also changing the best practices of handling data. And actually, another representative of the operations family is called MLOps, which basically merge operation with machine learning. So MLOps apply DevOps pattern to automate the lifecycle of machine learning models. And as you see here in the slide, both DataOps and MLOps can be seen as an extension of the DevOps methodology. DataOps cover the data journey, like data ingestion, transformation to data preparation. Then MLOps cover the second half of the journey, which include things like model training, model validation, model serving, etc. And then these two loops work together to complete the whole ML lifecycle development. So you might be wondering what has led to the rise of DataOps. So there are three main reasons. First one is the massive volume of complex data. So especially in the 2010s, there's a new revolution about big data with tooling like Hadoop or Redshift or Hive, MySQL, HDFS. Those kind of technologies, they're being born out to enable businesses to deal with large volume of data coming from various sources. Right. The second reason is what I call technology overload. Like, to answer a business question, the data needs to be in a format that you can understand and use for analysis. And you basically have to a lot of things ranging from data transformation to data cleaning to data security, data integrity, etc. And for each of those tasks, you need specific tools to handle different steps. And there's so many tools that you have to think about, and you might be overwhelmed with what choice to make, right? And then final reason I could say is the diverse roles and mandates. So basically, the people using the tools and technology to work on your data are very diverse, right? We have data engineers who focus on data preparation and data transformation. We have data scientists who need to worry about getting the right data for the algorithms. There's data analysts who care about building daily reports and data visualization. There's business manager who only think about the business impact of using the data. And then, bringing together these different technologies, processes, and people with different mandates will create collaboration overload and friction between teams. And that's why we need a DataOps framework in practice to make sure that these different personnel work together productively. Now, this figure in the slide provides a partial list of companies that are providing solutions in different areas that form the ecosystem of DataOps. So we have the infrastructure ops layer, which are consisting of tooling that monitors the data plane on top of it and initiating a response to the event or failure. We have the data plane here, which includes tools from operating system, there's ETL tools, data warehouse tools, as well as visualization and native AI system tool. There's also a metadata stack that creates a map of organizational data flow, tracks the flow of the data, and enforces access and data quality. There's a development layer, which included a lot of the development tools that you can use to manage complex processes that may include things like experiment and iteration, and then collaboration across teams and unit. And sitting all the way on the top, data products and services, which included tools that you can use to track business KPI and measuring products and services. So hopefully this slide allows you to understand, that this is a emerging stack, and there's a lot of different companies that are building tooling to support the DataOps landscape. So next, I want to argue for the case of why do we need to bring DataOps as a discipline into the domain of computer vision. The first reason is that in most real-world machine learning, including computer vision, the data is more important than the models. And this contrasts with academic machine learning, which emphasizes the modeling component rather than rethinking the data paradigm. There's a lot of low-hanging fruit that you can use to improve your data. All right, instead of fixing only on the model, you can do small things like data exploration, data curation, or data collection to get better data samples. And that eventually can improve your model performance instead of only focusing on investigating your model architecture or tuning hyperparameters, for instance. So I think that as a framework, DataOps can help you visualize, sample, and label only the important data points that are worth being labeled and yield most value with respect to a given task. So that's the first reason. The second reason is that unstructured data preparation is very challenging. As you can see in the slide, these are some examples of some data sets, red planes, that incorporates a lot of real and synthetically generated satellite imagery. And you can see that you have to be very, meticulous about how to label this data point. And overall, when you're working with image and visual data, the sample is high, but you also need to be very careful about drawing the right bounding boxes, for instance, right? And a lot of these things it requires domain expertise to understand how to what made up an actual labels. And because of that, preparing data for computer vision use cases are generally not for the faint of heart. And the third reason I would say is that building computer vision application is iterative. So this diagram that I put here in the slide represent the two separate loops of building a computer vision application. So you got the algorithm development loop, where you first build your algorithms, and then you measure the algorithms again in a data set, and then you measure that algorithms and learning from failure cases, right? So that's the first loop. And separate from that, you have what I call the product development loop, where you first build a product using some sort of microservice infrastructure in-house, and then you measure your product performance in production with some sort of monitoring or logging tools. And you learn from some failure cases with some error analysis using, maybe tooling to analyze your product performance in live performance data. So these two loops must work well together in order to, complete the whole computer vision application lifecycle things, right? And DataOps as a practice can help speed up the iteration of these two loops. For example, after building the algorithms right here, you can provide those algorithms into the engineers so that they can incorporate it into the computer vision products, right? And another way is that after you're learning from failure cases in production, you can tell the data labelers to sample and annotate more data set, only the one that your product made failure cases on, right? And then incorporate that into the algorithm development loop to build a new data set and then build new algorithms. And then with best practice in DataOps, you can basically, like I said, speed up these two different ways that these two loops can work together. So now I made the argument for the need of bringing DataOps into computer vision. I want to kind of went over some of the key principles of DataOps. And I think it's pretty crucial to understand these principles and then generalize that into the domain of computer vision, which I'll go in deeper details. So the first principle is to implement best practices for development. So basically, if you work with data, right, if you're a data engineer or a data scientist, for instance, it's important to follow this lifecycle guidelines as I outline here in the slide, because you need to write a lot of code, right? So it's good to borrow best practices from software engineering to make sure that your code is good enough to be put into production. So in practices, there are things that include version control, code reviews, unit testing, artifacts management, release automation, and infrastructure as code. And these are some of the open source tools that you can use to, follow this guideline, right? And applying these software development best practices for computer vision specifically is quite straightforward. To get started, I recommend this document by Google called Rules of Machine Learning, as well as this article called Engineering Best Practices for Machine Learning. And these two resources, they gather a set of engineering best practices for developing software system with a machine learning component. The second principle is to automate and orchestrate all data flows from the initial data source to final deployment. So in practice, you want to automate your deployment with a CI/CD pipeline, and then discourage any kind of manual data wrangling. And the best way to go about this is to run your data flows using an orchestrator for tasks such as backfilling, scheduling, and gathering pipeline metrics. There are a couple of well-known open source tools that can help you with the orchestration tasks that I put here in the slide, including Apache Airflow, Dagster, and Prefect. And applying CI/CD for computer vision is also quite straightforward. A great resource I recommend getting started is this article by the team at ThoughtWorks that talk about bringing continuous delivery principles and practices to machine learning application. The third principle is to test data quality in all stages of the data lifecycle. In practice, you basically want to test your data at the source by writing either data unit tests or, depending on the data sources that your pipeline is connected to, you might want to write schema tests, SQL tests, or streaming tests. And you then want to validate your data at different stage in your data flow. And then finally, you want to capture and publish some of the metrics across some of the stage that I just mentioned about. And the best way to go about this is you want to, reuse your testing tooling by building a common testing framework that can be standardized across your data team. And Great Expectation is a well-known open source framework that helps you with data quality testing. For computer vision, I think that continuous testing best practices is quite tricky because you not only have to deal with the quality of the data source, but you have to also think about like the quality of your label, because when you're working with image and video, you need to label the data point and making sure that the label is of high quality, right? So for things like this, you need to answer questions like, does the work of all your labelers look the same? Is labeling consistently accurate across your data set? And given that human in the loop component, when you need the actual labelers to collaborate with, building a testing framework for label quality is definitely, I think not an easy thing to do. The fourth principle is to monitor quality and performance metrics across the data flows. Then in practice, the first step is to define data quality metrics, which can be broken down into technical metrics, functional metrics, and performance metrics. The second step is to visualize your metrics to appropriate data stakeholders so that they can take meaningful actions using meaningful alerts. And in computer vision, I could say that this concept of monitoring quality and performance metrics is also called observability. And there's a couple of good vendors in space that have published a lot of thought leadership content about bringing observability practices to machine learning in general. The team at Monte Carlo, defines the 5 pillars of data observability to be include freshness, distribution, volume, schema, and lineage. And in the context of computer visions, that means how up to date the labels are updated, how the label can be distributed within an image, how big the number of images is, how the labels are visualized and formatted, and then finally how the image are currently being versioned. The team at Arise AI come up with the concept they call model observability, which is the process of collecting model evaluation in training, validation, and production environments, and then tying them with different analytics workflow to allow a practitioner to connect all these parts to solve the ML engineering problems together. Then finally, the team at Wild Labs proposed anatomy of an enterprise AI observability platform, which include key capabilities like telemetry collection, a time series database, a debugging engine, an anomaly detection engine, and a visualization layer. As you can see, there's a lot of companies in this space that are doing novel work with the goal of how can we monitor these different metrics that allows you to be more robust and reliable machining system in the real world. The fifth principle is to build a common data and metadata model. Most organizations in the real world, they face a significant challenge because the data comes from different sources, and then everybody looks at the system from different angle. And in practice, you want to create a common data model so that different people can identify similar terminology across different areas and across different teams, right? And then a more enterprise-focused approach to do that is to invest in a data catalog to share data knowledge more broadly across the data organization. And I put here in the slide, a couple of the open source tools that can help you with, this specific principle. So there are tools like dbt, very well known for allows me to combine different data sources and put them into a common data warehouse. And there are tools like Amazon, DataHub, and Marquez, or open source tooling that do the task of a data catalog, right? In the context of computer vision, I would say that data catalogs mean creating a repository of all your image and video data from different sources. And that includes also the details of the data structure, the data quality, the definition of data, the usage of the data, right? And ideally, you also can allow the users to access the metadata alongside the data itself. And when we're talking about image metadata, it really means a JSON object that describes your specific objects, right? And one thing that I think is still very hard is version control for unstructured data, right? Version controls mean you want to keep track of how your data evolve across time, maybe previous week, like present and in the future. How does it evolve? And when working with image and video, it can be hard to tell exactly how does it evolve. And solution like Pachyderm, for instance, is a promising option that is currently on my horizon. Ideally, though, I could say that a sophisticated solution for version control can keep track of the data lineage over time, and then that can also support with future data governance and compliance concern. And this is the sixth and the final principle of DataOps, which is to empower collaboration among data stakeholders. Basically, there are different ways to structure your data teams, but the best approach, I think, is to embed the data thinking into every functional team. And this is quite similar to the concept Agile principle in software engineering, where you want to build a cross-functional team with no division between key functions. And this team can define important KPI and metrics together, and then craft a shared objective with the business goal. And furthermore, to remove potential bottleneck for data usage, you want to use you also want to set up self-service data monitoring, and then democratize access to data. So that's got the high-level principle of how you can build cross-functional team when working with data. So while building computer vision application, I believe that an ideal DataOps team should be composed of the core function outlined here in the slide, and I go over in detail what these different teams and their responsibility in a second. You have the data labeling manager, and these people work in-house or offshore labeling teams to help scale the throughput of data labeling. They define labeling instruction, inspect the work of the labeling team, and decide how to handle complex or ambiguous scenarios. You have the data engineers who are responsible for designing, building, and maintaining datasets that can be leveraged across your machine learning projects. And then these data engineers work very closely with your machine engineers. You have the data curator, who are the expert in their respective data domains. They are capable of visualizing and manipulating your dataset, and their knowledge of the business goal as well as the machine capabilities can inform, the organization to prioritize the data curation efforts to improve your machine system. And finally, I would say, basically the head of DataOps, the leader who will oversee, these strategic DataOps practices. Their goal is to create an environment that allows different parties to access the data they need painlessly, build the skill of the business to draw meaningful insights from data, and ensure data governance. And they also act as a bridge between the DataOps team and other functional units, serving as a liaison basically between this team and then other teams, right? As my point, these DataOps teams work with different ML application team, right, across the organization. Maybe if you build, different sort of computation application, then this DataOps team is responsible for collecting data for these different use cases. Overall, I think collaboration process between the DataOps team and these different teams are still very ad hoc at most organization. Currently, there's no standard or best practices on how to facilitate this collaboration. And I think there's definitely room for tooling that can make this process more efficient. So in computer vision, as I kind of alluded through our conversation so far, DataOps mean building a high quality trained data set. So the next slide is my attempt to kind of draw a diagram picture of how this DataOps pipeline look like for a modern computer vision stack. So here's my high level thinking of how it looks like, and this results from a lot of different conversation with practitioners in the field, as well as tooling builder who are building tools to solve this problem. So let's go over this slide in more detail and kind of zooming in each of the building block, right? The first phase is what I call data acquisition. So that basically means you want to collect the data to use for your machine learning efforts. When you talk about data collection, that can range from you have to answer a question where to collect the data, and how much to collect initially, right? Besides data collection, you can also do things like synthetic data generation, and especially in computer vision, you can use technology to like generate synthetic data. And you know, this can be useful for some of the more for some of the use cases that doesn't have a lot of data at the first place. And finally, what I call data scavenging is the idea like you can scrape the internet or use open source data set, you know, online to get data for your development efforts. The second building block is data labeling. And in the context of data labeling, you have to answer a question like, who should label the data? How should the data be labeled? And what data should be labeled, right? And then getting this data labeling step right is extremely complicated because it is very slow, expensive, error prone, and often impractical, right? And I think that like my company, we start out with the data labeling solution. And so we think that efficient labeling operation could require a very rigorous process with like high performance tooling, its own life cycle, and as well as a validation process to make sure that, you know, you can actually get good labels for your data. The third phase is data debugging, which entails writing expectation tests to address the data preprocessing and data storage system. And essentially, these tests are what I call unit tests for your data. They are designed to catch data quality issues before this issue make their way into the DataOps pipeline. The fourth phase is data augmentation, which is a scientific process where you can manipulate the data by flipping it, rotating it, translating it, changing the color of it, right? And this is really novel in general. Like you want to augment the data in different ways. I think that there's still some fundamental issue with data augmentation though. Like you have to think about how to scale it to bigger data sets, how to handling some of the biases or corner cases, right? Things of that nature. The fifth phase is data transformation, which includes three separate steps. Data formatting, which is basically you want to format the data in a correct format, right? You have to interface with your data pipelines to, you know, make sure that you get the right format out of your data storage. You have to do things like feature engineering, right? You want to engineer relevant features. And recently, there's been a whole new category called feature store that just came out to, you know, address this problem. And then you have to do things like data fusion, which basically means fusing your data from different modalities, different sensors, and different timelines together. The sixth phase is data curation. And I think this is the most like underrated step in this whole life cycle because it's a very critical part that, you know, bridging the gap between the DataOps pipeline and the MLOps pipeline. Data curation is the idea that, you know, you only want to curate the most relevant data points to use for your development efforts. And in practice, you can do things like, you know, data cataloging. Basically, you want to, you know, sort the data by use cases, right? Or make it searchable by tags, or, you know, cluster data by a specific metadata. And then after you do the data catalog, you can do data structuring, data selection. You'll select the one that most relevant for your use cases. I will talk about the data curation in a more few slides, but I think this is like something that is emerging that we need to pay more attention to. After data curation, you go into your MLOps pipeline. You do everything that you want to do with your model. You want to build algorithms. You deploy your model in production. You monitor your model. Then finally, after you get a model in production, you want to close the loop, right? By doing a final step, what I call failures and edge case detection. And the idea here is want to, you know, measure your models in production, identify the cases where your model underperformed, and then after that, collect more data on those failure cases to get back, collect more data, and then go back to the data acquisition loop again to, like, you know, iterate your model development efforts. Basically, the second, like, V2, right, of your life cycle. Yeah, kind of complete the life cycle. And this is important because machine learning development is always going to be iterative. So you want to constantly get like a new version of your model all the time. And this is how you want to accelerate that feedback loop. So yeah, I hope this this diagram makes sense to you, and happy to share more details up to the webinar on how I conceptualize this effort. For the next 3 slides, I want to talk about the 3 specific data-centric challenges that any computer vision teams have to deal with. The first one is data curation, which is the point that I really just made in the previous slide, right? So to double click on this point, data curation is the process of discovering, examining, and sampling the data for specific analytics or prediction tasks. And then in the context of computer vision, data curation is like massively underrated because currently there's no streamlined method to understand what kind of data has been collected and curated into a well-balanced high-quality data set. It is very time-consuming, because it often requires domain knowledge about what does it mean, what this data means in this context, and then existing solution cannot keep up with the 4V of big data, which are volume, velocity, variety, and veracity in a very highly evolving, ever-changing data ecosystem. And finally, these solutions are quite narrow because they primarily learn from the correlation curve currently being present in the training data. I think that the function of DataOps platform for computer vision should have data curation capabilities that can enable data and ML engineers to visualize massive data set, discover and enrich data with ease, curate diverse scenarios, and integrate seamlessly with existing workflows and tooling. The second challenge is data labeling, which I also talked about in my previous slide, three slides ago. Yeah. So the idea here is like training a computer vision model, right? Requires like a constant feed of large and accurately labeled data set. However, this process requires a considerable time and capital commitment, especially since most of the labeling and QA is done manually by humans. So my team at SuperBI, we work on this problem for like several years now, and 2 major pain points, as I outline here in the slide, like manual labeling and QA is just painfully slow. Like human annotators go into each image and annotate them hand by hand, right? It's just not really scalable. And also when you're dealing with very domain specific data set, the QA is going to be very low. You think about like data points like image and video that you've never seen it before, right? Very rare cases, then you cannot like label it correctly, and so basically the label quality is going to be very bad. So I think that an effective DataOps platform for computer vision must address these 2 very expensive steps of labeling data and auditing the label. And in more detail, like this platform should be able to automatically label the data, identify and audit hard labels, and then use novel techniques such as active learning to verify, the human labels. And my company do a lot of this work on using automation best practices to address this issue. And then the third and the final challenge is what I call accounting for data drip. So the idea of data drip is that basically the training data set that you use to train your model in your local environment is going to be different from the production data that you use when you put your model into production, right? Because the data change all the time. It drips because it's come from a dynamic and time evolving distribution, and that means like when the data drift, your model performance is going to go down and it suffer, right? And it's going to decrease over time, leading to like business losing money, for instance. There are different causes for data drift, like upstream process change, data quality issues, natural drift in the data, covariance, for instance. And I think that a robust DataOps platform for computer vision should be able to detect data drifts and raise alert accordingly, analyze where and why the drift happens, and then adapt to drift and improve model performance. And and this pain point, it kind of went back into what I said earlier about observability platform, right? These companies, building tooling to address this data drip issues. And I think there's a lot of interesting work and technologies that currently being spun out to address this issue. For the final 3 slides, I will talk about the future of the modern computer vision stack, and basically like what does it look like in the future. I'll say that the modern computer vision stack gonna follow the footstep of the modern data stack. So if you work in data science, I would assume like most people in data science dojo does, you might have heard of this term called the modern data stack, being everywhere in the past 2 years or so. So the idea of the modern data stack is that it's a collection of cloud native tooling centered around a cloud data warehouse. The benefits of using modern data stack are like fourfold. Number one is ease of use. So these different technologies allow your teams to not worry about installing and maintaining technology. Everything is built around a data warehouse, and this minimizes integration pain points and silo data platforms that requires lots of effort spent shipping data around. Second benefit is wide adoption. So the modern data stack is constructed with the intention of upskilling data workers and removing the barriers between workflows. Third benefit is automation. So this stack allows you to automate a lot of different workflows. When integrated alongside different tooling. And the final benefit is cost efficiency. In the cloud, if you use a cloud services for your technology, you only pay for your usage, right? You pay for what you use. And then that has the benefit of allowing you to spend money on other more business critical activity. And then as the modern data stack continues to grow and evolve, there are different technologies and vendors that are entering the conversation. And I put here in my slide a diagram created by the team at Continua, which is a tooling in this stack that encapsulate some of the main functional areas of the modern data stack. We have the cloud data warehouse, data integration, event tracking, data transformation, BI analytics, data catalog, data observability, and data orchestration. And there's a very robust ecosystem of tooling that made up the stack. Now, I would say that machine learning and computer vision is subset machining is also evolving and converging in the same paradigm. What I call the canonical stack for machine learning. So my company, SuperAI, we are part of this newly formed organization last year called AI Infrastructure Alliance. And this alliance are dedicated to bring together the essential building blocks for AI application. And this canonical stack for machine learning brings together like efforts of different people, projects, and organization. And it acts as a focal point that allow these people to talk together, right? And the idea is to establish clean API, integration pain point, and open standard for how these different machining component of a complete enterprise machining stack can interoperate together. And the diagram that I put here in the slide is an early draft of some of the emerging patterns that we're seeing across like 100 members of the AI Infrastructure Alliance. You can see here there's tools on data engineering to orchestration pipeline to feature store foundation on-prem infrastructure to like model security. So there's a lot of different like component that made up this modern ML stack. And then I guess my hope is to in the next few years we can come up with a clear paradigm of how these two can work together, just like how the modern data stack has been in the last 2 years, as I show in the previous slide. And with that, like I also want to kind of like put this final slide here, which showcase the different startup opportunities in the machine infrastructure ecosystem. Like this diagram broadcasts some of the types of ML infrastructure companies divided into 5 major categories. So we have tooling that can make core workflows better, faster, and cheaper. We have tools that optimize communication. We have tools that improve production model reliability. We also have tools to augment data programmatically, as well as tools to remove the need for specialized ML engineers. So these categories are meant to deal with some of the existing mainstream ways of doing machine learning, right? And then my hope is that as more novel techniques, take off, this infrastructure will need to adapt as well. Like recently, we've seen a lot of novel technologies in like large language models, or OpenAI released Stable Diffusion, for instance. Like this technology, definitely changing the way we're doing ML, and the infrastructure to adapt with those need to adapt to satisfy that. And so if you like work in data and you think about the pain point that you currently have in your workflow, and you want to think about a way to build new tools and even do a startup around this whole ecosystem, now is a great time to do that. And you'll be in the same hand with like a lot of different other vendors that are solving the same problem, which is to improve the productivity of ML engineers and computer vision engineers, etc., to get more of those applications into the real world. And so with that, I want to conclude my talk. Thanks a lot for attending the webinar. Reach out to me via email if you want to get a copy of the slide. I'm also available on Twitter if you want to chat about high-level ideas about DataOps, about computer vision in general. And I also have a website when I publish a lot of blog posts about this topic. So if you want to check it out, feel free to follow me on there as well. I pass it back to Nathan.
All right, thank you, James. So I'm not seeing any questions yet. So what I'm going to do is I'm going to steal the screen from you. I'm going to do my little bit on the next webinar we have coming up next week, and then we'll see if any questions surface at that point. So, so Sam is asking about the session recording. So the recording, well, there is a recording, and we'll be posting it. We'll do a couple edits of it, take out any awkward pauses, that sort of thing, and then we'll make the recording available on our YouTube channel, as well as Data Science Dojo's website. So Fatima, if you could post the link to past events again, because Sam, that is where you can find all of our events very easily. So I'll have Fatima post that, or actually, yeah, is that it? Yep. So Fatima just posted the link, so you can find the recording there probably in a day or two. And then, but let's get my screen shared, because we have a crash course on transfer learning coming up next week. That is the right screen. Perfect. So next week, October 4th at 12 Pacific time, so the same time as today, we will be having a crash course on transfer learning, where we're going to be understanding the idea of transfer learning. We're going to learn how deep learning models communicate with each other, explore real-world applications, and then compare transfer learning with the human continuous growth model. So if transfer learning is something that you're interested in, feel free to join our crash course. We'll have Wasif Nadim. He's one of our Data Science Dojo's analytics content engineers. He's a real math nerd, so really fun guy to talk to about transfer learning. So October 4th, 12 Pacific time, crash course on transfer learning. I hope to see some of you there. And James, I am seeing a question come in, so I'm going to stop sharing. If you want to, feel free to pull back up your final slide again, if you still have it open, just so people know how to get in touch with you.
Yep.
Adama is asking, is it possible to get the presentation slides? And I think you mentioned for people to email you if they wanted a copy of the slides. Is that right?
I mean, I made the slide available, so just email me in the slide.
So alrighty. So thank you, James. Really appreciate you taking time out of your day to be here with us, and thank you for everyone else who joined. Appreciate you being here as well.